All right, we are going to kind of shift gears a little bit and talk about what similar figures are, which is what you've been doing already when you were talking about performing these dilations. You were creating similar figures, but I want to go into how do these differ from things that we've talked about in the past, and then also how do we take things from the past that we've gone over and use them when we are talking about similar figures. So there's a difference between things being similar to each other and things being congruent. What does it mean for things to be congruent to each other? Equal. What else did we maybe say if they were congruent shapes? There's like a lot of S's. We said it was same shape, same size. So that would be another way to think about congruence, is that when you were maybe manipulating the shape to have it face a different direction, you weren't changing the size of that shape. You were just moving it around. And we did review these terms earlier this week. So we'll see if you guys remember them. Because when we went over like the notation for dilation, I was asking you about the notation for some of these other terms that you worked with congruent figures. So I want you to think back, first semester, this is when you all would have gotten your patty paper for the first time. And we were working with some of these transformations. There was 3 of them that we did. Do you guys remember what they're called? Reflection.
Translation. And rotation.
Very good. So let's go ahead and write those down underneath here where it says which transformations guaranteed congruent figures, rotations, reflections, and translations. When we did any of those 3, the size of our shape was never impacted. The position was changed for some. Rotation, we turned the shape around on our graph. Reflection, we flipped it. Translation, we slid it around, but we didn't ever make it bigger or smaller. Okay? But then in that kind of same area, we called all of those isometric because they kept the same shape and same size. But we did talk about these non-isometric ones briefly. One of those was dilation, and the other one was stretch. Now, stretch is very different from a dilation because if you remember when we talked about dilations earlier this week, we said that it changes direction and all sides change the same amount, not just like one half or one part of the shape, okay? So when we talk about shapes being similar means that they're the same shape, but they're not necessarily the same size anymore. So right here where it says which transformations will guarantee that shapes are similar, go ahead and just write next to this. Similar means same shape but different sizes. We can still consider those 3 that we just talked about to be similar, because when we went over the scale factor earlier this week and talked about what happens if you make it bigger than 1, less than 1, and how it impacts the size of your shape, what did we say happens to our shapes if we do a dilation of 1? If it's equal to 1, it stays the same. So really when you guys were doing just a reflection or just a rotation, you maybe could have thought, well, I did dilate it, but it's a scale factor of 1, so there was no change that occurred. So these 3 things would still allow me to make similar figures, and now we can also include dilation to our list. So I'm just going to repeat writing these 3 terms down, but then we're going to add on dilation. Whoops, I skipped translation. Okay, now the third question is asking, how do we indicate that 2 figures are similar to each other? How do we know, looking at a picture, that we are dealing with a dilation and not like a stretch? On Monday, when we went over that activity on Desmos, I talked about how a dilation impacts the entire shape, not just part of it, like a stretch would. And I maybe use the word proportionally, which just means that all of the sides are being affected the same amount. So we took a scale factor of 2 times everything. We took a scale factor of 1/3 times everything. So I'm going to write down here for how we indicate is that all sides are changed proportionally. And in parentheses, I'm just going to write next to that, in all directions is what that means. So if I compare any two sides from the image and the pre-image that correspond to each other, there should be this constant scale factor that's showing up. Just like yesterday when you guys were doing that worksheet, you had to draw in your projection lines and then you had to find your scale factor. It didn't matter what point you went to from the center. You could have gone to the A and the A prime, B and B prime. You look at those slopes, they still should have been proportionally related to each other. If I reduce them both, they go down to the same amount. If I multiply both parts of my slope by the same number, it should give me my new slope. That's what that proportionally means. Now, something else I want to talk about, I'm going to scroll back up here for a second. So this is what we talked about yesterday. I want you to focus on the angles right now. When we did this one, did this angle from A to A prime change at all? No, this stayed the same. So this angle looks like it's congruent to itself because it's also overlapped and shared, okay? We can kind of see that anytime something is shared, it's going to be equal to itself. What about B and B prime? Do those look any different to you guys? Or like C and C prime, or do they look pretty close to being the same amount? And if you're not sure, I want you to think about, what did we say the relationship was between these two sides? They're parallel to each other. If we have parallel lines, and if this is like a transversal, we have those angle pairs showing up again. So remember, these are your parallel lines. These two would be interior, and like these here would be exterior. So I'm comparing these right now. Those would be like one's interior, one's exterior, but they're on the same side. Do you guys remember what we called those angles? Talking about like this one here and this one here. Started with a C, and remember that word? Corresponding. Those are corresponding angles technically in this picture. And the same thing is happening over here with C and C prime. Those are corresponding as well. So all the angles inside of your shapes when you do dilations should match. Your angles should never be getting bigger or smaller. If they are, you're not doing a dilation anymore. You're doing something else. So down here, I'm just going to add this on underneath where I wrote that in red. I'm going to put a little star by this, and I'm just going to say angles do not change. So your angles will be congruent to each other in your similar figures. Your sides may not be congruent anymore though, because if a dilation is happening, something could be getting bigger or smaller potentially. So they're not going to be equal, but they're going to be proportional. So down below, I want you to kind of take a look at this next chunk because we're going to start getting into actually working with these similar shapes. Look at just this to begin with. Does this look familiar to you guys? Have you seen something like this in the past? Okay, what's different about this one though? There's a minor change. We've seen that before.
I know, but like when we were doing it, when we did like with what we're doing on here, where we matched it with which one, we had like 4 letters on those ones.
Okay. There's also like one other thing. It's really subtle, Macy.
The congruence.
Yeah, this is a little different. When we saw this with congruent statements, what did this have in addition? An equal sign, okay? This isn't congruent anymore. When it's just like that little squiggly line, no equal sign, that means similar. It doesn't mean congruent, it means similar. So just underneath it, I'm going to write a note for that. This sign means similar. But it works the same way as what we did when we were working with a congruent statement. Your letters that are in the same position of the names should go together. They should match. So what letter should A match up with on the other triangle? M, and then B should go with R, and C goes with G. That stays the same. So when we're filling in these boxes down here, that's what we want to be using to help us fill them in. Now you will see when they talk about angles that they're still going to use a congruent sign for angles when you're matching those up because I already just said to you guys, angles never change. So the angles should be congruent. The sides, though, these look a little different than what we had before. You would have like AB is congruent to MR, and that's all we ever had to write for a congruent statement. But since we're now talking about similar, that part's going to change a little bit. So let's just begin with the angle, because I think that's the easier one, because it's just like what you've done before. You should say angle M is congruent to what angle? A. So I'm going to write angle A in that blank. Now the next two, when you get into the sides, we can't use a congruent sign anymore. They do have an equal sign, but it's not just saying that like these two sides are equal to each other. They have these fractions set up. These are also known as proportions. That's why I kind of used that word earlier, proportional, because it's going to be showing up here when we set these up. These are proportions, and we're trying to figure out what little piece needs to go in here. Read your proportion carefully, because they will change how they set it up. You're going to have 4 total like parts of your proportion. 2 of them are going to come from one triangle, and the other 2 are going to come from the other triangle. But you need to figure out where they're putting the pieces from the same triangle at. Are they both in the tops of the fractions? Are they both in one side of the fraction? Because they can switch that on you depending on what they want to do. So if you look at this one, RG is from which triangle? The first one or the second one in my statement? Second one. And GM is also from the second one, right? So they're setting it up where both pieces here came from the second triangle, which means both pieces here should come from the first. I'm given BC, I need to figure out what goes here. So now I just have to match it up with those letters. So what letters correspond to GM?
C.
Good, CA. Now they are giving you 2 blanks. I don't really care where you guys put it. You can put it in both, you can put it in one. I just need to see it written somewhere. Is this proportion set up the same way?
No.
Would they change?
Now it's 2 of each triangle on the bottom, 2 of each on top.
So like these go together? Is that what you're saying? And these go together? Because like MR and MG, those both came from the second statement. So this is coming from the first triangle. Again, but it's written differently than what we saw in that last one. So you're not going to want to compare AC and fill something in over here. You're going to want to use this MR and compare it to that first triangle in order to fill in this blank. What letters should go with MR? Good, AB. It's not a major difference, but switching how they write it out can impact how you read the proportion and then which triangle you're supposed to grab from. So make sure you read through those proportions carefully. You take a second to just ask yourself, how are they setting this up? What 2 pieces do I already have from one side of the triangle so that you know which other side to pull from? I want you guys to do the next 3 by yourself. I'll give you a minute to write those out. Okay, what'd you guys say for your first blank? Angle T is congruent to? Good. The second one? QY, very good. And the third one? Good. All right, any questions on filling those in? Okay, come down here to the bottom now. We're going back to the graph. What they're asking us to do is figure out a sequence of similarity transformations that would map one triangle onto the other to show that they are similar. You guys have done something like this before, but when you did it, you were dealing with congruent statements. Like you were dealing with 2 congruent shapes, and we were trying to get them to land perfectly on top of each other. We're still doing that for this, but there is going to be a dilation that has to happen in order to get them to be the same size. So when we do these, and when we did these in the past, you guys used patty paper sometimes to help you out with these, especially if you had to do rotation or reflection. If you still have a piece of patty paper that you would like to use, you can go ahead and get that out. If you need a new one, just put your hand up. Mr. Akers has some back there in the box. He can get you a new piece. You don't have to use patty paper, okay? If you know how to do these and like just put put it on the graph, you know where it's going to go. You don't have to rely on this, but it is a really nice tool to have in case you don't see it super easily, if you need maybe a little bit of help, okay? All right, to begin these, I'm going to put a little note at the top here. I always go small shape to big shape, okay? So I'm just going to put that up here at the top. I'm going to go small to big. There's a couple reasons why I do that. One, consistency. I want to make sure you guys know how I'm doing it up here so that you can follow along later when you're looking at it. Two, if I'm always making the shapes bigger, my scale factor is always going to be greater than 1, and I have less of a chance working with fractions. Okay? And if you don't like fractions, then I would suggest that you also go small to big, because most of the time your scale factor is going to be greater than 1, and you don't have to worry about trying to figure out if it was a half or a third or whatever. Now, the first thing we need to do sometimes is make sure that our shapes are facing the same direction. So on this first one, are these triangles facing the same direction? They're kind of going opposite, aren't they? I want them to be facing the same way. Like I want them to both be leaning in the same direction here. Now I'm going to move the small one because I said I'm starting with the small. And I need it to be kind of inside this shape here. I want it to overlap, because if my shapes overlap, that center point where they overlap at is what I can use for my center of dilation. Because yesterday, even that one that I scrolled back up to when we talked about the angles being equal, if I have a point that's overlapping, we always use that as our center point because it would be the same for both shapes. So does anyone have a thought on how I can move this triangle to get it to be facing over here? We could use a rotation. We could do a reflection. You could do either one. The nice thing about these problems is that there's usually more than one way to get there. And I don't really have a problem with you having different answers than I have. As long as I can follow your movements and they work, you're going to be fine. Okay, so make sure that when you're writing it out that you're being very specific about what you did. So if you did a rotation, what would you be rotating? Like how many degrees? Any idea? We could go either way. We could go all the way around this way, and so that would be 270 degrees. Or I could go this way, but it would be negative 90 now, right? Because if I go clockwise, that's technically negative rotation. If I did a reflection, what would I reflect over? The y-axis. Okay, so either way is going to get me probably in the same position. So I'm going to go ahead and I'm just going to go with a reflection because that notation is a little bit easier to write out, I feel personally. What letter do we use for reflection? Little r. And then you guys said y-axis, so I'm going to write y-axis next to this here. And then remember when we did these with congruent statements, I always wanted to see after you wrote your notation what shape you did it to so I could follow the shapes that you started with and ended with. So we are starting with triangle. We'll call it RGO. I don't care how you name it. You could switch the order of those letters around. And then what I'm actually going to do is sketch on where that reflection would go so I can kind of see it on the graph. So I'm going to put G, that would go here, R would go here, and that O would stay where it is because it's on the line that we're reflecting over, so it's not going to change position at all. Which is good, because remember I said I wanted a point to overlap because that helps me with my dilation. So they're facing the same direction now. Now I need to just figure out how did it get bigger, what number did they multiply by to do my dilation, and let's go back to thinking about our slope from yesterday. The point that they overlap, I'm going to use as my center, and I need to count from either that origin point to the G, or I need to count to the R. It doesn't matter which one I go to. If we go O to G, what's my rise over my run? 3/2. I'm just going to write that down over here in the margin. So I'm talking about this distance here. We went up 3, we went over 2. So now to get my second slope, I should go O to what letter? B, because that should correspond with G. What's my slope there? 6/4. So what scale factor happened here? 2. So I'm just going to write there scale factor of 2 because I have to multiply 3 and the 2 by a 2 to get to 6 and 4. And I just need to write that down here. Okay, let's practice writing in our dilation notation. What letter do we use for dilation? Good, capital D. Next comes my center. What letter did I use for my center point? O. And then what was our scale factor we found? 2. And I still did that to triangle RGO. And then if I did that to this, if I blew this up twice as big, it should look exactly the same now. So you're done. So key things here are get them facing the same direction. They need to overlap on a point. Now I just chose to use that O because they were already connected there. When you have shapes that are a little bit more disjointed, like the second example that we're going to go through, you have a little bit more freedom to decide what point you would like to have overlap. And then you always use that overlapping point as your center. So if we come look at this next one, are they facing the same direction? Yeah, so I don't think I need to do a rotation or a reflection. I do need to move the shape over. So that's using a translation. And then like this, I said, you kind of get to choose how you want to do this. You could have E line up with O. You could move it so that the P lines up with the A. You could even do T and H and have them line up with D or B. It doesn't really matter which point you want to move. All that's going to change is the vector that we're using when we slide the shape over. Okay, so what letters would you guys like to get to line up? E and O. That's what I would do. So how do I move E so that it lands right on top of O? What directions does it need to go? Right. How many? 8 squares. Okay. I'm only focused right now on getting E and O to match. So I need to move it 8 squares over to the right. That's using a translation. What letter do we use for translation? Good. Capital T. And how do I write the vector?
It's an angle sign, and then it's 8, comma, O, or angle sign.
Yeah, I always call like less than greater than signs. They kind of look like those symbols. Okay, but yeah, 8, comma, 0, because all I had to do is go right 8. I don't have to go up or down at all, and that should get E to line up with O. So now I'm going to put that on my graph so you can see how they overlap. So E would be here now. Okay. Now let's figure out our dilation, because once we get them lined up, we just have to figure out what's the scale factor that occurred here. So my center point is still here because this is where they overlap. And you can choose what letter you would like to count to. Anyone have a preference? You want to know what I would pick? I pick the bottom because you're just counting horizontally. You don't even have to worry about rise over run. You're just looking at those numbers. How much of a difference or space is between these two? 2. And how much is from here to here?
6.
So how do you go from 2 to 6? You multiply by 3. Now, if you actually set it up rise over run, you're not going up or down at all. So it'd be 0 over 2, and then it'd be 0 over 6 if I'm just going from O to P and to the A. But either way, I'm going to still get my scale factor of 3. That's what I would do. The less counting I have to do, the better. Okay, so now what I'm going to do is write this out. Again, we use capital D. What was the center we used? O, and we just said our scale factor was 3. And what should I have put in parentheses after this? Because I forgot to do that. I don't know if I want to call it squares because not all sides are the same, but you're on the right track. What do we call the name of all 4-sided shapes? Quadrilateral. Okay, so I'm going to say quad. I'm going to shorten it. Quad, and then I'm going to name this. Now, I don't care how you name this. The only thing you can't do is jump corner to corner like diagonally. That's not allowed when naming the shapes, but you have to go around them. And so down below, I'm just going to write quad. And I'm going to say ETHP. But you guys can have those letters in a different order. All right. Any questions on that?